Good morning guys. Today we are going to start a new topic, that is in module 3, torsion of shafts. Now already you briefly have studied in what is meant by torsion, everything in your mom. I am basically going with a small definition. What is torsion? Torsion occurs when any shaft is subjected to a torque. This is true whether the shaft is rotating or stationary. That means both the cases it is possible, because sometimes it is stationary, sometimes it is rotating. Okay, the torque makes the shaft twist and one end rotates relative to the other. That means if you apply a small amount of a torque, what happens? One end rotates, other end is also rotates in opposite direction. This means one end is in clockwise direction, means generally another end will be in the anti-clockwise direction. Inducing, due to this what happens? It is going to develop a shear stress in the element on any cross section. Shear stress in the element on any cross section. See how to do finite element formulation of these kind of shafts. For that, I represented it first as figure. Just see a shaft, okay, a prismatic bar or rod, okay, of length L, that is also represented by dx, okay, then diameter small d, okay, x is the coordinate, y is the y coordinate, z, then g is the rigidity modulus, t is the torque applied, and gamma max is called shear strain developed due to the shear stress developed in the body, okay, d theta is a small arc, okay, that means really a small change in your angular displacement. Okay, then this is also written here, say same figure I retraced, but I had shown that here if you apply torque in one direction, another direction it will be in the anti-clockwise direction. Now this entire thing, if you analyze it in FEM, we can consider this entire thing as a simple one-dimensional element. Simple one-dimensional element. See, one-dimensional element means what? We have only one displacement at each node. If you observe the displacement, what here? Theta 1 is the displacement at this node and theta 2 is the displacement at this node. Related to the torque, T1 is the torque applied here, T2 is the torque applied here. See, one torque is in clockwise, means obviously another will be in the anti-clockwise direction. This is your length of the shaft. Now how to formulate this? What is the equation I want to use? See, if you use T1 and T2 are they called the end torques at node 1 and node 2. Okay, theta 1 and theta 2 are called end twists at node 1 and 2. Now what is the general equation you're going to use? The general equation is theta equals to a1 plus a2x. Similarly, like what you used it in bar, u is equals to a1 plus a0 plus a1x. Similarly, I'd use theta equals to a1 plus a2x. You can use same equation, no problem. If in next one, if you take it, this will be theta is u is equals to n cube. That r, this will be written as theta into n theta. This will be written as, I think you can write like this, theta is equals to n1 n2 into theta 1 theta 2. See, the global displacement u will be equal to, you will write it like this, nu or nq, n1 q1 plus n2 q2, like this you can write it. Okay, n1 n2 into theta 1 theta 2. Now come to next, from the figure, the arc length AB is given by, see whatever the arc length AB is there, that AB will be taken as a gamma max into dx. This if you simplify it, you can write it, gamma max will be equal to what? R by dx into d theta. At any position we can take, in any position the gamma max means maximum shear stress, but if generally if you take it, what is gamma? Gamma will be equal to, we can replace R, we can keep it as it is, dx will be L, and d theta will be taken as theta 2 minus theta 1. Why theta 2 minus theta 1? I am taking theta 2 is positive, theta 1 is negative. Okay, theta 2 minus theta 1. Now, for any linear elastic isotropic materials, if you take it, shear stress and shear strain, we know that what is the relation? Sigma equals to into epsilon. Similarly, if you take shear stress and shear strain, that is shear stress equals to rigidity modulus into shear strain. Now, if you simplify this, what you are going to get? Tau will be equal to G into, what is here? Gamma is R by L into theta 2 minus theta 1. Theta 2 minus theta 1, because gamma already we obtained. I am taking this equation number 1. I will write this as equation number 2. Now, next come to also from torque equation. If you take torque equation, we have, what is torque equation? T by J equals to tau by R equals to G theta by L. From these two terms, I can write that T will be equal to, because I want torque, T will be equal to tau into J by R into J into R. Now, if you simplify this, substitute equation number 2 in this, what happened? See, J by R, it will be, keep it like this. Next, G into R by L into theta 2 minus theta 1, theta 2 minus theta 1. Now, if you see here, theta 2 minus theta 1, what happened? See, your R and R will cancel. What is remaining? G, J by L. See, I will write the equation torque, that is T is equals to, I am going to write the equation, T is equals to G, J by L into theta 2 minus theta 1. I am going to write the equation G, J by L into theta 2 minus theta 1. I will take this as equation number 3. So now in equation 3, from the figure, what we have, second figure, that means second figure means figure 2. You can take this as figure 2. Figure 2, this is your figure 2. Okay, from figure 2, if you observe T1 and T2, I am taking here T2 is positive, that is in clockwise direction, and T1 is in negative. T1 is negative. Now, if you take it from this condition, first, and from figure at node 1, T is equals to minus T1. If T equals to minus T1 means what happened? Minus T1 is equals to Gj by L into theta 2 minus theta 1. This can be written as T1 is equals to Gj by L into theta 1 minus theta 2, because if you multiply minus sign, theta 1 comes here, theta 2 comes here. Or if you take minus sign outside, Gj by L into theta 1 minus theta 2, minus minus cancels. This is your T1. Similarly, at node 2, what is T? T is equals to T2. I am taking positive. Now, if you take it, T2 will be equal to Gj by L theta 2 minus theta 1. Theta 2 minus theta 1. Now, take this as equation number 4 and take this as equation number 5. Now, if you combine equation number 4 and 5, if you observe, if you combine equation number 4 and 5, T1 and T2. First T1 equation, what is this? T1 equation Gj by L theta 1. See what is required? Positive 1 minus 1. If you observe this equation, if you follow this equation will be like this: T1 into Gj by L 1 minus 1 into theta 1. T2 is equals to Gj by L into theta 1 is minus, theta 2 is plus. Now, if you observe, this is the equation. This T1 T2 Gj by L 1 minus 1 minus 1 1 into theta 1 theta 2. Now, this will be looks like this. This is called T into K into theta. Now, here K is called torsional stiffness matrix. Torsional stiffness matrix for shaft. Torsional stiffness matrix for shaft. Stiffness matrix for shaft. Or this we can write it as Gj by L into 1 minus 1 minus 1 1. This is equals to K torsional. That means stiffness matrix for a torsional stiffness matrix for element, or K torsional matrix will be equal to Gj by L into 1 minus 1 minus 1 1. See, it is almost similar to your bar element. This is how you should determine a torsional stiffness matrix for a shaft element, and this is a simple procedure for determining your torsional stiffness matrix. The method what we adopted, we call it as a direct method. Earlier what we solved for your bar element is, it is called it as your potential energy functional method. Thank you.